ion collider, which might happen about 2030. We want to search for exotic hadrons. These are states that are impossible to construct in the quark model, in the sense that two particles, a quark and an antiquark, can have a certain set, a limited set of quantum numbers. So anything that doesn't have those quantum numbers is called exotic. They would probably involve some gluon degree of freedom, some explicit gluon degree of freedom, a valence gluon degree of freedom. And that would make a very different type of hadron. It would be the first time that we'd ever seen a force field playing the same role as matter. We want to exploit the opportunities we have, provided by new data, on the elastic and transition form factors of hadrons, to learn about the running of the couplings and masses, and look for correlations that appear inside of hadrons. Mesons, normal mesons, probably don't have correlations as such, but any system with more than two bodies can have correlations in it. Nuclear physics tells us that when correlations are possible, they almost always happen. So we should expect that the wave functions for baryons and hybrids exhibit or possess correlations that make them very different than the simple cavity models that people have traditionally employed. We would like to study the valence quark region, precision experimental study, to try and work out just what the valence quarks are doing inside the hadron. You can also look at the gluon sector and the C-quark sector, and people are. This is a different type of physics at very low Bjorkane X. It answers different questions, and perhaps this behavior is universal inside all hadrons. But when you talk about a proton or a neutron, you really specify what its valence quark behavior is. So understanding the valence quark behavior is the same as understanding all of the observable properties of that hadron, because these are the defining characteristics. And we would like to explore and exploit the opportunities to use QCD as a precision test for physics beyond the standard model. Since the LHC at high energies, at the energy frontier, has not shown us anything new, people are turning to another direction. They are looking at high luminosity, high precision physics as the place to search for physics beyond the standard model. It's a completely new direction, and facilities are being built now to use QCD physics as a test for beyond the standard model quantities. But overall, these challenges can all be gathered together into these three questions. We want to use theory and experiment to study how confinement is realized, how it can be defined, how it's related to the generation of masses in the standard model, and what is the connection between them. Are they the same thing? Are they completely different? As I've said, I think they're the same thing, but I can't prove it mathematically yet. One of the facilities we're using for this is Jefferson Lab in Virginia. It is about 3 hours drive from Washington, D.C., south. And it was agreed to build this machine in 1984. The construction began 3 years later, and in 1994, 10 years after the initial approval, we had a facility that could reach 4 GeV, the electron beams, and the cost was about $1 billion. If we take this as a model for what might happen with an electron ion collider, then we might get approval to build this in 2020, so it might start to operate by 2030. And that'll be a new generation facility for studying QCD in all of its guises, mapping out perhaps the three-dimensional images of the proton in a process that will start in about 10 years' time. The goal of the JLab facility was and is to work out what holds nuclei together, starting with hadrons, and with the ultimate goal, as I said, to try and find out how QCD can generate nuclei. Simple ones to start with, but then the more compound ones, even up to lead, but that's probably a long way away. And how this is all connected with the gluons and the quarks. JLab uses elastic scattering for many processes, and it tries to extract from that information on how these quarks and indirectly gluons are distributed within the hadrons. And one of the predictions of perturbative QCD that actually Stan gave us many years ago now is that given cross-sections will behave with Q squared in a very special way. There'll be a part that comes about from just dimensional counting, a part which is 1 over the scale squared to some power n, where n counts the number of elements, valence quark elements inside the hadron. And there'll be some logarithmic scaling violations, which are calculable. You can predict what this anomalous dimension will be. This number here picks up a plus or minus 0 or a plus 1, depending on whether a spin has to be flipped in the process. But it's basically just counting the number of particles in the system, valence particles. This part is the feature which is peculiar to QCD. It's the logarithmic correction to the scaling laws. You can get scaling laws in many simple ways, but we didn't know we had QCD until we, for example, measured scaling violations in deep inelastic scattering. If you look in the particle data group, for example, and study the F2 structure function for the proton, you will see that over many orders of magnitude it appears flat at one particular set of kinematics. And that was the place where SLAC actually looked to begin with. When we developed the capacity to look closer and vary the kinematics, we saw these logarithmic variations in this scaling law. And those logarithmic variations are exactly what we saw, or what we predicted, from perturbative QCD. And that's what gave us the confidence to say that QCD looks like the theory for the strong interaction. Without those logarithms, it could have been anything. QCD predicts those logarithms in a special way. It counts the number of gluons and the number of active quarks. It was initially imagined that you would see these scaling laws and the scaling violations at about 1 GeV. So after discussions and arguments, it was decided to build JLab so it could reach 4 GeV. It should take you to the point where it was possible to see those scaling violations. In the 10 years following the beginning of operations at JLab, many results were produced, many fascinating experimental outcomes. This is one of them. It was unexpected, and I mentioned it before. In particle physics, people imagined that the proton was a simple object, typically just 3 valence quarks in a cavity, all in an S wave. Under those circumstances, the proton would have a very simple structure, and you would expect that GE divided by GM, properly normalized, would just be 1, would be a constant. And the old data from SLAC was roughly consistent with that. So people thought, right, we understand it. It is a very simply structured object. But JLab has much greater luminosity. There is a way of measuring this ratio GE over GM that is completely different to that which was used at SLAC because of the increased luminosity. It's a polarization transfer measurement. The beam is initially polarized, and you transfer that polarization to the target, and that cross-section is directly proportional to the ratio GE over GM. And what JLab showed was that this ratio is not 1 at all. It drops very quickly away from 1. And that's the strong pointer that something is happening inside the proton. It is not a simply structured object. This type of behavior suggests that there are strong correlations inside the system, that the wave function is very complicated. This also means that there's no sign of parton model scaling out to at least 8 GeV squared. Because if you do reach the domain where parton model scaling is working, then there are certain strict rules for how GE and GM will behave. And these are not evident here. So you must go beyond at least 8 GeV squared before you can see the scaling in the proton. One might expect, based on simple quark counting ideas, that you'd have to get to 20 GeV squared for the proton. But for the pion, you can do this at a lower Q squared, as we'll discuss. In 2004, it was agreed that, well, we need to go higher in energy to try and expose these scaling laws, to try and test QCD for the first time in an elastic scattering process. We've been doing deep elastic scattering for a long time. We had seen many of the features that QCD should predict, but there are this entire array of predictions of QCD for hard exclusive processes that we would like to test. because they're testing both their information about perturbative QCD and their understanding of the wave functions of the hadrons involved. So they're testing our pictures of non-perturbative QCD too. In 2014, the 12 GeV commissioning beams were operating. The machine was upgraded at a cost of about $370 million, and it had a whole array of new experiments to do. The era of experiments at 12 GeV began last year. I think 2018 was the first year in which a whole array of experiments at 12 GeV were completed. And what one is able to do as you get to this domain of between 0 and 12 GeV is start to push your way through the part or the domain where you have non-perturbative physics evolving into perturbative physics. So to start to map out this transition. You have a typical picture of a proton. You have a couple of, well, 3 valence quarks for the proton, and then all this structure inside, and you want to map out this density of partons within the proton, say, or within the pion. I'm going to talk about the valence quark structure. It's definitive of a hadron because, for example, it's how you distinguish a proton from a neutron. When you say the proton has 2 up quarks and 1 down quark, you don't mean that. You mean it has 2 valence up quarks and 1 valence down quark. And the neutron has 2 valence down quarks and 1 valence up quark. That defines the difference between the proton and the neutron. The gluon structure of the proton and the neutron might be the same, deep in the interior. The C quark content might be the same, might be different, we're not sure, but the valence quark content is certainly different. This expresses all of the macroscopic quantum numbers of the bound states, charge, flavor, baryon number, and so forth. And via evolution, the valence quark structure determines all of the backgrounds of the LHC. If you know the parton distribution functions at, say, 4 GeV squared, LHC is operating at 16 TeV squared, at 100 TeV squared. You want to evaluate or evolve these PDFs from the low scale, because as you do get to the high scale, they occupy all of the low X region. So they provide what you need to compute the backgrounds, to test the standard model. So actually knowing the valence quark distribution functions is critical to understanding what the LHC is producing. In the foreseeable future, we will have fairly precise measurements of the valence region in the proton and the neutron, so this proton and the pion. What we need to do also is compute them. There has been a history of just parameterizing distribution functions. They are essentially non-perturbative. You can't compute them in perturbation theory. But unless you can compute them some way, there's no way that you can tell whether or not your parameterization of the data has any connection with the underlying theory. You can make up a parameterization, you can ignore what QCD would tell you, and it might fit the data. Now, is that because the data has errors and you're not sensitive to the QCD physics? Or is it because QCD is not the right theory and there's something messing up the connection between what you think is QCD and what is the data? So unless you can compute the distribution functions, you will never know whether the experiments are validating or falsifying QCD. No amount of data will be useful unless you can compute these distribution functions. One example is, or can be found in these formulae for hard exclusive processes. So the simplest one, or one of the simplest, is a statement that for any pseudoscalar meson, the elastic electromagnetic form factor will behave in a very special way for q squared bigger than some scale q naught squared. It will be q squared times that form factor is the running coupling for the theory multiplied by the electronic decay constant squared multiplied by a moment of the wave function squared. It was promised that JLab would verify this, and people were looking for that. In that formula, of course, is the pion's wave function. So you have to be able to calculate that if you're going to test whether this formula is working or not. And it's the light front wave function that you need. Stan this morning will explain many of the benefits of using the light front. I will just have one transparency to highlight these things. A Hamiltonian formulation of quantum field theory is provided by working on the light front. That's setting x plus equal to 0, choosing this plane for quantization of the theory. The idea of doing it is that you have quantum mechanics like wave functions. That means you have real probabilities. On the light front, the question of particle number conservation doesn't hurt you because it's conserved. The number of particles initial and final state is the same, so you can have an overlap of wave functions. That makes it possible to talk about probabilities. If I tried to do this in a covariant formulation, a sort of equal time quantization of the theory, then as I mentioned in the first lecture, you strike the wave function, that impetus will create more particles. So the final state will have a different number of particles. You cannot overlap psi prime with psi and expect to have a probability. So if you really want a probability interpretation, if you really want to say, I have a density of particles, you need to use a light front formulation. So when people tell you that they have computed or measured or extracted a distribution function, they are talking about a light front distribution. When people talk about what is the spin content of the proton and what carries it, they are speaking explicitly about in the light front or on the light front. It's nothing to do with the proton in your body which is at rest. It's a very different statement. And the way of going, translating from the light front distribution to the equal time or rest frame distribution is non-trivial. In fact, no one can do this yet going in that direction. You can go the other way. So you have a quantum mechanics-like expectation value, can be defined and evaluated. And that's what I just said. Particle distribution functions are correlation functions that equal light front time within this initial surface. So you can now take this idea, and we want to compute the wave function. I've been talking about how to compute a beta salpeter amplitude for a bound state. Some of the exercises show you how to solve a beta salpeter equation using the contact interaction. In the contact interaction, you can also compute the PDA, the particle distribution amplitude for the pion. It's a constant. Because the theory, the contact interaction, doesn't exchange momentum, then the two partons don't talk to each other. So the probability that they'll carry any amount of momentum is the same. So it's a constant. The PDA for the pion is just 1. That's one extreme. If the quarks were infinitely heavy, then they must both be carrying half the light front momentum of the bound state. So the PDA will be a delta function. So you will evolve from something which is momentum independent, which is flat, to finally something for infinitely massive quarks, which will be a delta function. Somewhere in between lies the real world. There is a way of taking the beta salpeter amplitude for any bound state, in this case the pion. You reattach the legs. This is an amplitude. To get the Schrödinger wave function, you put the legs back on. This is the quark propagator and the antiquark propagator. That is the analog of the Schrödinger wave function. If it were possible to take non-relativistic limits of the beta salpeter equation, then the thing that would match onto the Schrödinger wave function would be this S gamma S. You can verify that mathematically. So you take now the wave function, the Poincare covariant wave function for the pion, and you project it through the pseudo-vector channel onto the light front, which is what this delta function is doing, and you obtain the light front distribution amplitude at leading twist for the pion. To get from here back to here is impossible because you've lost too much information. But you can go from the fully covariant wave function onto the light front. Using realistic beta salpeter amplitudes for the pion that I've illustrated in the last couple of days, remember it's connected to the quark mass function, so if you know the mass function, you can compute this projection. You will find out that the answer for this quantity is proportional to x to the alpha 1 minus x to the alpha with the power alpha equals 1/2, approximately. Now, if you did QCD and worked at scales that were ludicrously large, grander, bigger than the scale that the LHC can reach, then the distribution amplitude for the pion must be x times 1 minus x. I'll do it here. 6x 1 minus x is the asymptotic profile of the pion's distribution amplitude at leading twist. Now, when Stan first wrote about this with Peter Lepage, he said that this is the asymptotic form, 6x1 minus x, and he showed what could happen to the pion form factor with that amplitude and with a couple of others, just to illustrate what the possibilities were for the outcomes. After that, people forgot about the other examples that were presented in the paper and always said that the Brodsky-Lepage prediction for the PDA of the pion and the pion form factor was obtained with this asymptotic distribution. So there was a whole array, many decades of people saying that the Brodsky-Lepage prediction was wrong because they couldn't measure it experimentally. What we now know, and Stan during his lectures will talk about another way of reaching this conclusion, is that at a real-world scale, the PDA of the pion is not 6x1 minus x, it's actually squashed and broadened. What I'm showing here is two different ways of computing this using continuum methods in QCD. Different truncations. I explained that when you use these continuum functional methods to analyze a quantum field theory, you have to make a truncation to break the continuing tower of diagrams. We have the simplest truncation, which is like Hartree-Fock. We call it rainbow ladder. But for the meson systems, we can go far beyond that leading order truncation. We have an essentially non-perturbative way of improving upon the truncation. And you see that both truncations, the improved one and the simplest one, agree semi-quantitatively. The PDA is crushed and broadened. This PDA shows that the real-world pion wave function is squat and fat. And you can connect this behavior to the way the quark mass function is running. Because of that Goldberger-Treeman relation, the rate at which the quark mass... Yes, please, Robert. dB, it means that dynamical chiral symmetry breaking improved truncation. dB for short. When we first wrote about this, the first author's name was Daniele Benossi. And the referee thought it was the Daniele Benossi truncation. We had to explain it's not. The running of the quark mass function determines just how crushed it is and how wide it is. If the quark mass function were a constant, then this would be a constant. If the quark mass function runs, then the PDA is different. So this is the first computation to directly expose dynamical chiral symmetry breaking and its pointwise expression on the light front. So, yeah, go ahead. So yes, this is the leading twist one, which appears in the leading twist formula for the pion form factor. Correct. So what you have now is this leading twist component is normalized by f pi, for example. Let's take f pi. That's part of the content of f pi. F pi is an order parameter for dynamical chiral symmetry breaking. That can't happen in perturbation theory. So you see that the so-called leading twist part contains a lot of non-perturbative information about the physics in QCD. And there are sub-leading twist components. They're also non-perturbative. The evolution equations will take me from this real-world PDA, which involves lots of non-perturbative information, even though it's still the leading twist PDA, to the asymptotic form, which is truly the parton model operators. So it's the statement is that you've changed from parton model operators to dressed quasi-particle operators to produce this leading twist PDA. And all that information is contained there. You have resummed infinitely many diagrams. This pion in here is a coherent state. Otherwise, the normalization would be zero. No, no. You can add something if you like.
So the trick of the Drouin-West one is that you choose the plus current, you take matrix elements, and then you pick the frame where Q plus is equal to 0, allows you to actually then give you general formula in terms of the conservation of parton number, Craig said. So then you don't change parton number.
And that's
The trick
that,
is, so it's a trick of a special frame that's ingenious that allows you to get a general exact formula.
the point of it is you have taken your parton model, and these operators have to evolve. The evolution equations take away all the dressing to get you 6x1 minus x. At any normal hadron scale, the leading twist PDA is not just a parton-antiparton. It can't be, because there's no bound states then. Bound states involve binding. There's an enormous amount of information contained. If I look at the twist 3 part of this, for example, there's a twist 3 PDA. That is the chiral condensate. And that's not, it's an essentially non-perturbative object. These are all bound state properties. Isolated partons. So even though it's leading twist property of a bound state. So I'm taking a bound state wave function, I'm projecting out leading twist information. All of that is there. All of the strong non-perturbative dynamics is still present at leading twist. That's the whole point. You're taking projections, in a sense, slices of the non-perturbative wave function. You're not taking just the two-parton part. You're projecting that, a piece of it out, but it's all determined by the non-perturbative part of the wave function. Otherwise, it'd be the conformal limit is, in a sense, a conformal theory. So there's no interactions, there's no bound states. So it's a misapprehension to imagine that there's a simplicity in the leading twist. The leading twist is a slice of the fully interacting wave function. Yeah. F pi is measurable. F pi is an essentially non-perturbative quantity. It's an order parameter for dynamical chiral symmetry breaking. F pi is 0 in the chiral limit unless chiral symmetry is dynamically broken. And that says that the wave function at the origin would be 0. This projection would be 0 unless chiral symmetry were dynamically broken. All sorts of values, all sorts of projections, leading twist, twist 3 and so forth, would all vanish if there were no bound state structure. That's what it means. So these wave functions are truly wave functions. They are horribly complicated. If I choose to reflect this in a parton model expansion, that's why when you use the light front directly, you can't compute this, because you are doing a Fock space expansion. I've had to go through the whole procedure of developing a quantum field theory in the continuum in a Poincare covariant fashion, so I could resum infinitely many diagrams without a Fock space truncation, and then I've made the step by projecting back onto the light front. People tried for 30 years to go the other way.
To say that in terms of Fock component, this wave function sounds infinitely many Fock components in some non-perturbative fashion.
That's right. It's the wave function.
So
And I project that leading twist. So the leading twist part comes, I project through this operator, and I use a projection on the light front. This is going to give me the leading twist component. If I put another operator here, I can get a next, so twist 3 component.
So could one, let's say, understand this wave function as you said before, okay, if I'm correct, some burst particle or quasi-particle creation operator acting on some vacuum.
Yes.
So could one, starting to say bare particles for infinitely many-dimensional space on the line, but as you said, one needs to truncate to control it or to do any calculation. Then one change the basis in some, following some evolution from bare particles to rest particles, in order to arrive to a basis that represents two degrees of freedom, and there is no need for truncation on the line. Would it be possible?
That is the dream of many people. So that's what Ken Wilson was trying to do when he was at Ohio State. He was trying to develop a practical scheme, beginning with a light front formulation of theory, to construct what do you call it, a constituent quark along those lines, trying to develop the sort of quasi-particle operator in a constructive way. What we're showing here is that the Dyson-Springer equation, in fact the gap equation for the quark, is doing just that job. But we do it in the covariant formalism because it's easiest to solve it there, because I can resum all the diagrams. So my truncation there is a different type of truncation. I don't do a Fox-based truncation. We do a diagrammatic truncation that says at some point I'm going to break the connection between an endpoint function and an n+1 point function. That still gives me infinitely many diagrams, and it still allows me to develop a coherent state. Now that coherent state, as we saw in this picture, this was the simplest coherent state. I improved upon the truncation, the connection between all the diagrams, and that changed the wave function a little, but not dramatically. Mm-hmm.
So you said that, referring to this equation for the lifetime wave function, you said that if are possible to take non-relativistic limit to arrive to some sort of Schrödinger equation
Yes.
for this wave function. Do you know what kind of Schrödinger equation you could take?
What I said is you would arrive at the Schrödinger wave function. I cannot tell you what the potential is that would go into that Schrödinger wave function. That would be a different question. I would have to, it's not clear to me that the operations commute. I can solve the fully Poincare covariant theory, and I can obtain the beta-beta wave function. If I were in a domain where I had a valid non-relativistic limit, it might be the case that I could take the non-relativistic limit of the interaction and produce the same wave function. But I could not guarantee that.
I remember the top model,
Mm-hmm.
two-dimensional large QCD. You can write beta self-equation for a wave function, and you can take it to the form which describes a massless particle in a square wave.
Mm-hmm.
It's interesting. So, and the wave function is maybe not at that form. It's not x times 1 minus x. It's more complicated. It's probably something like sine,
Mm-hmm.
more or less. So maybe, no, I think we maybe know if there's something similar for the notion.
Yeah, so I think that the 't Hooft model, that when you work in dimensions less than 4, things don't change smoothly. So there are no smooth evolutions from 2 to 4, and so insights are lost. It's not easy, if at all possible, to develop insights about 4 dimensions by looking at a 2-dimensional theory, or those insights are limited. So that is the end of a 30-year story. There was a long argument about what the form of the pion PDA is, and now we know that the Continuum studies predict the pion and also kaon PDAs are broad concave functions. Lattice simulations now are developing techniques where they can actually compute the pointwise behavior of a distribution amplitude. Before they could compute only moments. Now there are ways that you give them access to the pointwise behavior. And they are improving all the time. What they confirm qualitatively is this feature, that they are broad and they're concave. It means there are no bumps in the middle. There are no camel humps. And that was the source of argument. All S-wave light quark mesons have this type of PDA. And there are many predictions that you can verify from this. I'm just going to make one aside and say, where does the Higgs boson play a role in any of this? You want to ask the question, when does the Higgs mechanism begin to influence mass generation in the strong interaction sector? And this is the picture that you can draw. We have the light quarks. They're forming a pion-like bound state, and their PDA is broad and squashed. There are the heavier quarks. This is a charm, anti-charm system. I can compute the PDA for that too, using the same way. It is squeezed and growing. As I said, that as the bound state's constituents become very, very massive, this approaches a delta function. Continuity says that there's going to be a point in the middle where they pass through the asymptotic profile, where the broadening from dynamical chiral breaking is being compensated by the crushing of the Higgs mechanism. And that happens at the strange quark mass, or very near. I'm not saying it's exactly the strange quark mass, but in the neighborhood of the strange quark mass, you pass through the point where emergent and explicit mass generation are roughly equal. And so it says that if you study physics that compares light quarks with strange quarks, you can expose dynamical symmetry breaking effects. Ratios, comparisons between the up and the strange quark effects will expose this. And that means pion form factors and kaon form factors, for example, or distribution functions of pions as compared to distribution functions for kaons. I was going to speak about this yesterday, but I didn't, and I won't have time to do it today. So let's continue the picture of the pion and its elastic form factor. In the 7 years after JLab began operations, an experiment was completed that measured the pion form factor from 0.6 out to 1.6 GeV squared. Since that time, more data was taken and pushed it out to about 2.5 GeV squared. And the experimentalists were looking to reproduce this result, which was thought to be the perturbative QCD prediction. That means the prediction obtained with the asymptotic profile for the PDA. When they saw this result, they said that they were still far from the transition to the Q-squared region where the pion looks like the perturbative QCD parton model prediction. There was disappointment and surprise. At that time, in the year 2000, there was a continuum QCD prediction as well, but it stopped at 4 GeV squared. And the reason it did was because the algorithms they were using were very simple-minded. They just took a computer and they tried to calculate the integrals. Because the quark propagators and the gluon propagators have unusual singularity structures, then the complex plane is full of surprises. And the algorithms they were using couldn't cope with that. So the calculation just broke down and they couldn't go any further. There was a factor of 3 discrepancy between the calculation, which described the data, actually came out before the data, and this prediction obtained with the asymptotic profile. This led many people to believe that they would never see parton model scaling and scaling violations by studying the pion form factor. Plans were made to use the 12 GeV upgrade to push this out further. And the experimentalists believed they could reach 6 GeV squared with that level of error. And they were asking the question, was this ever going to turn over? And could it get anywhere near that prediction? In the meantime, new techniques have been developed to analyze these processes. The same techniques that you use to compute the PDA for the pion can be adapted to calculate the form factor for the pion. With these new algorithms, you can develop new insights. The first point was to compare the data with the real QCD prediction, not that obtained with the asymptotic profile. The real QCD prediction actually sits up here. When you use the PDA appropriate to the scale of the experiment, which is 4 GeV or GeV squared or 6 GeV squared, the actual hard scattering formula result is here. And if you use the same algorithms to predict the form factor at all Q squared, you can go beyond that limitation. If you know how to handle the singularities in the complex plane, then this is the curve you get from that continuum prediction. This continuum prediction has truncations, but it doesn't involve a twist expansion. This is the leading twist formula. You can see they're only 15% different. So now you have confidence that an experiment at 9 GeV squared will see this turnover and this evolution. And that would be enough to validate the hard scattering formula, because it's the logarithmic corrections to the hard scattering formula that validate QCD. If you drop the alpha of Q squared, then you would just have the simple vector meson dominance prediction. This would be Q squared times F goes to a constant. And existing data is well described by a simple vector meson dominance pole. It's when you see the breakaway from the vector meson dominance pole that you've seen the impact of QCD in the hard scattering formula. So that would be the goal. The experiment at 9 GeV squared is going to take place? Following these calculations, the experimentalists reanalyze the potential of the JLab facility at 12 GeV, and they expect to be able to obtain a result at this level of accuracy, this precision, at 9 GeV squared. And that would be enough to distinguish from the continuation of vector meson dominance and hence validate the 1980 prediction for the pion form factor. Can we be more confident? Well, people using lattice QCD would also like to predict the pion form factor. The continuum prediction is one thing. They would like to predict it too. The problem is that lattice QCD has competing challenges. To deal with a pion, they need large lattice volume because the pion is light. They need small lattice spacings to reach large Q squared because the Q squared you can reach is proportional to 1 over A squared. So to go to large Q squared, you need very small a, where a is the lattice spacing. And you need very high statistics. Form factors for composite particles drop quickly. The signal becomes very small. You need to be able to distinguish the single from the lattice noise. So you need to have very high statistics. These competing constraints mean that lattice calculations at the moment cannot reach the physical pion mass, but they can be performed at larger pion masses. And these panels show an array of calculations. This calculation is produced by the people working at the University of Adelaide. This calculation is produced by the people working at the University of Glasgow. This is at a pion mass of 0.47 GeV, which is 3 times the normal pion mass. This is at 4 times the normal pion mass. Remember, for mesons, it's the mass squared that matters. So this is 10 times too large, and this is 20 times too large. The curves you see here are the continuum analyses. If you have a continuum approach, the pion mass is not a challenge for you. You can work in the chiral limit or at any pion mass. And you can study the evolution of the pion form factor with that mass. And these curves that you see are predictions. They're not tuned to anything here. What we see is that the Adelaide results are consistent with the continuum prediction. The Glasgow results are consistent at small q squared, but are breaking away at larger q squared. We don't know why, but we've also gone on to analyze the JLab results at a different pion mass, and they agree too with the continuum calculations. So there's an emerging picture that lattice calculations at larger pion masses are confirming the evolution of the pion form factor with mass, and hence adding weight to the prediction of the real pion mass result, and hence confirming that the lattice, that the experiments will measure the pion form factor accurately. Yes?
How does that link with the
Sorry, yes. Some of the points I was going to make here are the fact that as you increase the quark mass, and as you increase the pion mass, the pion form factor takes longer and longer to reach the conformal limit or the asymptotic profile. It's obvious. You put an external mass in there, you're going to drive yourself away from the point where the scale becomes irrelevant. So you cannot use large mass pions to check the hard scattering formula because your PDA becomes farther and farther away from the PDA you want. So it's the wrong way to go. You have to be at the real pion mass to have any hope of validating the hard scattering formula. So in achieving this, then, we're demonstrating that modern lattice results can be reinterpreted as confirming the continuum prediction of the physical pion mass that provides more momentum to the challenge of measuring that 9 GeV squared point. So it is likely, yes?
Sorry, another question. So your prediction for the pion form factor, can you show whether it has the right asymptotic limit?
Yes. Okay, so it seems likely that within the next 5 years, we will, using the JLab facility at 12 GeV, validate the 1980 prediction, Brodsky-Lepage, Efimov and Radushkin, for the pion form factor at large Q squared. And large Q squared here is 8 GeV squared. The reason it's 8 GeV squared for the pion and 20 GeV squared or 18 GeV squared for the proton is just because the pion has 2 quarks in it and the nucleon has 3 valence quarks. You take 2 objects, you give the dressed quark each half of the momentum that's coming in. You're going to get that divided by q squared over 4 equals 2 because the quark mass function runs, and that gives you 8. The same thing for the proton will give you 18. So you can understand the difference in scales between these two things. So that will verify the expression of dynamical chirosymmetry breaking in the pion wave function, because you will validate the picture of the pion PDA as being a broad concave function. There is much more that could be said about meson physics, a whole array of physics about light quarks, mixed quark systems, heavy mesons, and so forth. But you have the idea of how you study the meson problem. I wanted to give you some feeling for what it's like to study a 3-body problem, to study baryons in QCD. The constituent quark model picture we know evolves into this complicated picture with a whole parton distribution array inside. We want to treat this problem in the continuum. And there's an analog, the hybrid and exotic mesons. They don't have the quantum numbers of a simple quark model. People speculate that they have some additional gluon-like degree of freedom, however you might define that. And that makes them a 3-body problem as well. So the techniques you develop for solving the baryon problem might be the same techniques you need to properly understand the hybrid and exotic meson problem. It could be a valence quark, a valence antiquark, and valence glue. You want to be able to formulate that problem mathematically and then address the solution. To study the baryons as a 3-body problem, a Poincare-Covariant approach is to adopt a Faddeev equation. It's the analog of the beta-salpeter equation in the 3-body sector, and you study how the quarks scatter from one another. And this is the images of the usual Faddeev-like truncation with 2-body subchannels being resummed and 3-body forces being neglected. What you want is to correlate the properties of mesons and baryons, their ground states and their excited states, using a single symmetry-preserving framework. And that means, as usual, that you want Poincare covariance and you want to satisfy the Ward-Takahashi identities. You have symmetries everywhere. You want to preserve them. GA, for example, the axial coupling of the proton, that is fixed by symmetries. That constrains it. The fact the proton has charge 1 is fixed by symmetries. If you mess that up, you'll have to fine-tune the charge of your proton and fine-tune all sorts of other things. So symmetry preservation is important. I've expressed how dynamical mass generation plays a big role in the meson sector. It plays just the same role in the baryon sector. In fact, as we saw, there's a way of seeing that the proton mass is just 3 times the dressed quark mass at the origin. So you need to put these things in there to understand the proton dynamically. So you want an approach that can connect meson physics and baryon physics without any difference, and without any seams, a seamless connection. And the picture that you have of a proton is also very simple and equally complicated. If I just took a 3-body picture, I have 3 quarks inside the proton. Every one of the quarks is colored. If I take any one of the quarks away, I no longer have a bound state. So this is the Borromean-like picture of the proton. No 2-body subclusters inside the proton are bound. All 3 have to be there. They're interlinked. This must be a key part of the baryon structure. So you can view the proton as a Borromean bound state, a system composed of 3 bodies in which no 2 form a bound state. The picture of the proton is more complicated, as we've seen, because of all these particle-antiparticle pairs that are coming, but this idea is still being communicated. So the question then becomes, where does the binding between the valence quarks come from in the proton? Well, one approach would be to imagine a lattice simulation again. People have been looking at what types of interactions can exist inside a baryon. They put 3 sources, infinitely heavy sources of color charge inside the system, and they move them around. And people have argued that a Y-junction type of flux tube picture emerges. And they think this is great because a Y junction looks like a 3-gluon vertex, if you use a bit of imagination. And so you think that this is a signal that the non-abelian character of QCD is driving this binding, that this 3-gluon vertex is somehow intimately connected with the binding in a baryon. That would be true if these infinitely heavy quark pictures were equally valid in the real world. But as I just showed before, QCD is very different to that with light quarks. The static quark approximation is invalid. It does not let you draw any connection with light quark physics. So that's not the picture you should be using for a proton as a bound state. You can throw it away. Any interaction that is capable of creating a Goldstone mode as a bound state of a light-dressed quark and an antiquark, and also reproduce the measured values of their physical properties, will also generate strong correlation between any two dressed quarks contained within a nucleon. That's simply saying that anything that can make a pion will also make two quarks, any two quarks inside the proton, like each other, correlate. This happens all the time in nuclear physics. There are strong correlations in nuclear physics. This is BCS theory working for you. BCS won the Nobel Prize for making a very simple observation. Anytime there's a little bit of attraction between two fermions, they will condense. They like to do it. So you guess that two-body correlation will play an important role inside the bound state. That's what these statements say. No realistic counterexamples are known. Fermions always like to form pairs. With this in mind, and the predictions for many years that diquark correlations play a role, there have been lattice simulations. These are some of the early ones. There have been more since then. And they're looking for correlations in the diquark channels. You can have quarks scattering in the scalar channel, the action vector channel, and other channels as well. And what you can see is as you look at this scattering, you do see strong correlations appearing, in particular in the scalar channel, this black one. The scalar diquark channel has a very strong correlation in it. In the action vector channel, there is a strong correlation, but it's weaker than the scalar channel. There are correlations, in fact, in every diquark channel. The strength depends on the quantum numbers, but the curves all look qualitatively the same. So the simulations that we have from lattice QCD that look for dynamical generation of correlations see such correlations. Moreover, if I imagined I was dealing with SU2 color, so two colors of quark, then diquarks would be color singlets. They'd be the baryons. So they have to exist. They would exist as asymptotic states and form mass-degenerate multiplets with the mesons composed from the same light-flavored quarks. That means that the scalar diquark would be massless in the presence of the pion. This explains, because going to three colors doesn't lose the memory, why the scalar diquark is so prominent. It's the pion's partner. And it's very strong in three-color QCD, the pion bound state, and that correlation persists at three-color QCD. The scalar diquark must be very strong. Vector mesons exist, so you're going to have action vector diquarks, and that pattern continues. The bulk of QCD's particular features can be traced to the running coupling. These 3 and 4 gluon vertices are very important. You know that they contribute to the gluon propagator, and I demonstrated how they contribute to the effective charge. So this vertex, the 3-gluon vertex, should be the dominant factor in producing all of the interactions that we use. It's this 3-gluon vertex, in a sense, that is driving the existence of this correlation between the quarks. The running of the effective charge makes these correlations strong. So you're building an enormous amount of non-abelian dynamics into the pion, and also, by analogy, into these diquark correlations. So all of the non-abelian dynamics you know must be there is being used to form these correlations. The Faddeev equation that we're going to use was introduced 60 years ago, in 1960. This is Faddeev himself. He died about 13, 14 months ago in February 2017. 18, I think. That equation has been mentioned 47,000 times in the scientific literature. It's a much used equation in many branches of physics, but it's been rarely used in quantum field theory. It treats the quantum mechanical problem of three bodies scattering via pairwise potentials. It reduces that scattering to a sum of three terms, each of which describes a solvable two-body bound state problem. So in a sense, this approach allows you to reduce the three-body problem to a sum of two-body problems in the absence of explicit three-body forces. It can be generalized to the three-body force problem, but that is more complicated. But you can do it this way, so it simplifies the problem. This formulation of that problem has a unique solution. That's what made it important. You could solve the three-body problem exactly. There is an analogous approach to the three-valence quark problem. In this case, you need dynamical mass generation, and you need symmetries. And that means you must generalize the Faddeev equation, take it from quantum mechanics, and make it valid for quantum field theory. So you generalize and make a Poincare covariant Faddeev equation. It has similar diagrammatic structure, but it is like the connection between a Bethe-Salpeter equation and Lippmann-Schwinger equation from the Faddeev equation to the Poincare covariant version. Dynamical chiral symmetry breaking has an enormous impact on meson properties. You must include it when you describe baryons. The proton mass probably comes from that in large part. It's a quantum field theory effect. And just like mesons appear as a pole in quark-antiquark scattering in a 4-point function, you can consider the 6-point scattering problem, 3 quarks in, 3 quarks out, and look for the pole in that, and that gives you the Faddeev equation. And that equation will sum all possible exchanges and interactions that can take place between the three dressed quarks. So in a sense, it's the continuum generalization of how a lattice simulation would extract the mass. The lattice simulation will put 3 quarks as a source, 3 quarks as a sink, and watch them propagate. And they look for the exponential decay because in configuration space, the exponential decay is the same as finding the pole. So we in the continuum look for the pole because we work in momentum space. This picture is the Faddeev picture. 2 quarks correlate to form this diquark. You have tight diquark correlations. That simplifies the three-body problem to a collection of two-body problems, which you then solve iteratively. The three-gluon vertex is not an explicit part of this quark-diquark Faddeev equation. It is buried inside the diquark correlation. The dominant effect of the non-abelian multi-gluon vertices is to form these correlations, and then the baryons are formed from the sum of the diquark and the quarks breaking up and reforming. So the diquark here breaks up, that quark joins that one to form the new diquark, and so forth and so on. So you have a very necessary rearrangement of the correlations. This is actually forced upon you by the Pauli principle. You could not make a three-body bound state consistent with all the symmetries we know of for fermions if the diquarks were elementary, such that they were point-like with the quarks inside them never getting out. Because you'd be making these 2 quarks special. You wouldn't be symmetrizing the three-body wave function altogether. So the diquarks must break up. So you have 2 quarks, we'll call them the U and the D in the proton, for example. The U and the D, one will break up to join the other quark. So I have UD diquark becoming a UU diquark, and this quark goes by itself, and that keeps happening time and time again, iterating. So you have a very dynamical picture of the diquarks forming and breaking up all the time. And that changes the character of the wave functions enormously. So the baryon is in a compound system whose observable properties and interactions are primarily determined by the quark-diquark structure. This has observable consequences. It makes predictions. An experiment pushing to larger Q squared is able to check those predictions. All right, I think I'll stop here and we'll take a break for 5 minutes or so. Okay, very good. Let's begin again. Okay, so we have one conclusion from all of this is that the baryon, proton in this case, in its ground state, must have both scalar isoscalar and pseudovector isotriplet diquark correlations. Any calculation that produces a correlation in the scalar channel, scalar diquark channel, will also produce a correlation in the axial vector channel. It can't be avoided. If you do it, if you drop the axial vector diquark, you're making a mistake. People make models like that, but it's not a realistic picture of the proton or the neutron or so forth. The relative probability of the scalar versus pseudovector diquarks is a dynamical statement. So model independently, you can say that both are there. But the ratio, the relative strength of one compared to the other depends on the dynamics. How strong the correlations are in a given channel, how heavy are the quarks, how much dynamical symmetry breaking they have, and so forth and so on. So that number can change. So it's a prediction of the framework, and it's empirically verifiable. It can be tested. So this nucleon and all the other baryons is described by a Poincare-covariant Faddeev equation. It's a Borromean bound state in which the binding has two contributions. One part is expressed in the formation of the tight diquark correlations, and that comes from the non-abelian character of QCD. And the other part is associated with this quark exchange. It's driven by the Pauli principle. The diquarks always break up, and this adds additional attraction to the bound state. So it's the proton's mass, for example, is not just the sum of the diquark mass plus the quark mass in any simple way. It also includes a binding energy derived from this quark exchange. That exchange ensures that diquark correlations are fully dynamical. No quark holds a special place. Each one participates in all diquarks to the fullest extent allowed by its quantum numbers. And the continual rearrangement of the quarks guarantees, amongst other things, that the nucleon's dress quark wave function complies with Pauli statistics. These are not your grandfather's diquarks. It was an idea in the 60s that the proton should be simplified as a bound state problem because you couldn't solve the three-body problem easily. So they decided to introduce point-like diquarks. A point-like diquark to be bound with another quark, the proton two-body problem. There was a reason for doing this, or many reasons. One of them was just practicality. Another one has continued to emerge. The quark model, with 3 quarks in it, predicts many baryon bound states, ground states and excited states. And then, and even today, many of those bound states have not been seen experimentally. It's called the missing resonance problem. We have all of these predictions from 3-body models and all of these states that are not seen. One answer to that is to reduce the number of degrees of freedom in the proton. If it's a 2-body problem, then the number of excitations is much smaller. And so you have many fewer baryons. So you can solve the missing resonance problem by imagining that the proton is effectively a 2-body bound state with very tightly correlated diquarks that don't break up much. These diquarks here are not frozen. They break up. As a consequence, this, in a sense, this is an approach that can test the old idea of diquarks. If I use these diquark clusters, and they are loosely correlated, I will make predictions for observables, for the spectrum, for scattering observables. And requiring agreement with that body of observables will tell me just how closely correlated or not are these diquark correlations. So I can turn experiment or use experiment as a constraint on the picture that one's developing. Yeah.
This is the formula.
Sorry?
This formula.
Yes.
Suppose you have, let's say, 3 giant quarks or 3 photon quarks.
Yep.
Will there be such correlation like quarks?
Yes, the correlations persist. The correlations, this is new work. People have long imagined you could study heavy baryon systems, again as 2-body problems. People thought that if you had a CCU system, for example. So same, an omega C, or omega CC, so CC and an S. That you could solve this problem by imagining the two C quarks formed a point-like diquark cluster, which was the source for the other particle to move in.
Why C quarks?
That's the same question I asked. Why would it be the CC that formed the cluster? The answer was that it was the easiest problem to solve. But if you do the calculation today and allow this diquarks to be dynamically generated and to have this dynamical mechanism for rearrangement, then you find that the dominant correlation is not CC. It's actually C with the S. The lightest correlation provides the strongest contribution to any bound state, typically. So yes, in bound states, in baryon bound states with some heavy quarks or all heavy quarks, diquark correlations still play a role.
You said something about diquark being partial.
That's right. So that it's part of the argument. So the scalar diquark in the isovector channel is a partner of the pion. If I imagine that I'm dealing with CC, for example, the partner there is the E to C. The E to C is bound. So there's going to be a correlation in the CC diquark channel as well. None of these diquarks are asymptotic states. They never get out because they're color anti-triplets. But that doesn't stop them from correlating inside the color singlet bound state overall. So the predicted probability that we will see is that the baryon, the proton, has both axial vector and scalar diquarks. The other diquarks are not important in the proton ground state. And the ratio of axial vector diquark to scalar diquark is about 0.6. So the scalar diquark is dominant, but there's a very measurable, a very important, yes?
Since you mentioned the Borromean system,
Yes.
so if you calculate this just for the dipole, so if you do the calculation and look for bound state to the pole channel, do you find a bound state pole or not?
If you solve the quark-quark scattering problem, you find no pole. You can make truncations in which you do find a pole, but you know that truncation is bad because that would mean there would be an asymptotic diquark state that I could see in my detector, which of course I never do. So what you can see then is that in the color singlet channel, going beyond this Hartree-Fock approximation doesn't do much. There are cancellations between the quark line and the antiquark line. But in the color-color channel, the leading order truncation is poor because the cancellations do not happen, because this is a color anti-triplet instead of a color singlet. So to study these, what you find is that when you solve the scattering problem with a good kernel, there are correlations. So the correlation function rises, as we saw in the lattice simulations, it rises, but it doesn't reach a pole. It just has a broad structure. So there's no bound state in the channel, there's a correlation in the channel. So you might sense, in terms of physical particles, it's a sort of resonance structure, a resonance appearance in the scattering. And because these diquarks are dynamical, this typically produces a picture in which the number of states is the same as the three-body quark models produce. And, in fact, the same number of states that modern simulations of lattice QCD are producing. So it does seem that there are many more baryon states to be found. So experiments are underway to try and discover these new states. There are very simple states missing. Even in the decouplet sector, in the first radial excitation there are states missing. Even the ground states are hard to find. The particles with strangeness. And it's because the final states involve more than two particles. And you have to unfold three-body final states, for example, even more body final states, to see this resonance. So it becomes a difficult empirical challenge to find signals for these new or missing baryons, for those with strangeness. So the point is that by using such an equation, you can express confinement and dynamical chiral breaking, and it's a prediction of dynamical chiral breaking that you will have strong diquark correlations within baryons, scalar and axial vector in their ground states. So what does this equation mean? This object is the analog of the beta-Sopit amplitude. The pion has a beta-Sopit amplitude. Here I have a Faddeev amplitude. The diquark is composed of strongly dressed quarks. So the same quarks that make up the pion are going into this diquark correlation, these strongly dressed quarks with their running mass functions. This quark has to go across here because that exchange guarantees that my amplitude will preserve the Pauli statistics of the bound state. With scalar and actual vector diquarks in the problem, I'm going to have S, P, and D wave correlations inside the proton. It means that you can never have a proton that is just an S wave system. It's basically saying that Poincare covariance demands that the bound state proton contain orbital angular momentum. Where you put it depends on how you choose to formulate the problem. You can ascribe this to gluons if you like, if you choose to use the parton model basis. But if you use the dress quark basis, you'll find that it's locked up in quark-diquark orbital angular momentum, because that's what this Faddeev amplitude represents. You solve for the diquark by studying the sort of Faddeev equation, or the beta-Sopit-like equation for quark-quark scattering. And why should that produce any reliable results? Well, the point is that if you consider the leading order truncation, as we just discussed, we have a gap equation for the quark, we have a beta-Sopit equation for the meson. If I look at quark-quark scattering instead of quark-antiquark, all that happens is I get a factor of a half here. And that explains why the correlations in meson channels demand correlations in diquark channels as well, because the coupling is just suppressed by a factor of a half. Any interaction that describes mesons will also generate diquark correlations in the color antitriplet channel. It does not happen in the sextet channel, because there you get the wrong sign. The interaction is repulsive. This object is a spinner, and there are things to solve for. We have a free particle spinner and the dressing function for that spinner, both in the scalar channel and the axial vector channel. This is an equation for that quantity, so a matrix here and a matrix here. And there's a kernel, the standard type of linear integral equation for a bound state. Act with the kernel on the state to recover the state. The eigenvalue is 1, and you find the bound state p squared. This kernel has this quark exchange structure. So a particular example is the leading term, 1, 1. And that says that I have a quark and a diquark. It propagates the diquark, and the diquark breaks up. That's what this beta-Sopit amplitude with the bar means. It's not being bound into the channel, it's breaking up from the channel. So the one quark goes away, that's what this S transpose is. The quark is moving across here. And then it connects again with the other quark to form a diquark correlation. So that diagram is this piece of mathematics. You have a diquark propagator and a quark propagator, the breakup, the transition, and the recombination. And there are momentum arguments just for momentum conservation. I just went through this. Those, that exchange, this, and this. Every one of these entries has a simple matrix structure, and the kernel has similar entries in the other channels. So it's a simple matrix equation to solve. If you combine everything, you arrive at a linear homogeneous matrix equation for these amplitudes. Just like a Lippmann-Schwinger equation, just a little more complicated. Again, you can make this transparent by working with the contact interaction. We know how to do that. You've seen it. You regularize it in a sensible way. You ensure you can preserve the symmetries. And from there, you can, in just 1 or 2 lines, derive the sort of equations that form the qualitative picture that you use when you solve the full problem, with all the exchanges, all the momentum dependence, and so forth. So it's a useful tool to develop insights. And the simplest case is what I'll illustrate. It's the delta baryon. That is the first spin flip partner of the proton. The proton has spin half. I must correlate my quarks in a very complicated way to turn 3 spin half objects into a spin half object. I have to correlate these carefully. If I have a spin 3/2 object, so a spin 3/2 object made from 3 spin half objects, it's very simple. All the quarks must have their spins pointing. That's the simplest state. That means the beta salpeter amplitude or the Faddeev amplitude will be much simpler for the delta than it is for the proton. That's why you illustrate the problem with the delta. The delta is spin 3/2. It's also isospin 3/2. And that means you can't have a scalar diquark in the delta, because you can't combine 0 isospin with half and get 3/2. So it says that the delta must involve just the axial vector diquark correlation. The ground state is flavor symmetric. They contain only axial vector diquarks. And now we'll solve this Faddeev equation, or write down the Faddeev equation with contact interaction, following the rules that we've introduced before. We do one more thing. That's the so-called static approximation. And what that means is I take this exchanged quark and I just keep the mass term. I drop the other piece. If I don't do that, then solving this contact interaction Faddeev equation is almost as complicated as solving the real Faddeev equation, because I have momentum transfer in this line. So my amplitude, the Faddeev amplitude I obtain, will be momentum dependent, describing the correlation strength between the quark and the diquark as a function of momentum. I don't want that complication, so I'm going to replace this by a static exchange. Is it any good? Well, it introduces errors. You find that it doesn't allow for enough binding. So you put a parameter in there to say, let's put some binding back. And then you get a simple approach to the problem. Then you can ask the question at the end, how realistic is this? That's not so important as developing an insight into how to solve the problem. This approach produces diquark correlations which are momentum independent and Faddeev amplitudes which are momentum independent. That makes for dramatic simplifications and lets you see through into the core of the problem very quickly. Delta baryon has 4 charge states. I've listed them here. This is the simplest one, 3 up quarks with charge +2. Since all bound states will be degenerate because I have isospin symmetry, then I can use the simplest one, just 3 up quarks. And isospin symmetry is good to better than 3% in the strong interaction, so I can use this. The contact interaction Faddeev amplitude for the delta has this structure. Here's the diquark propagator piece. Here's the beta salpeter amplitude. And this is my solution function for the delta, acting on a Rarita-Stringer spinner. If you have a spin 3/2 object, you have a spinner with a Dirac index. They're easy to work with. They satisfy certain conditions. My diquark propagator is a vector particle, so it must have a tensor structure like this. And the quantity tau plus is just this diagonal matrix in flavor space, because I'm turning up quarks to up quarks to up quarks. So I want to have the maximum isospin. So it's an isospin raising operator all the time. This Rarita-Stringer spinner is necessary to define and represent a covariant spin 3/2 object. It satisfies the Dirac equation. There's an index. And these 2 constraints tell you how to fold that index into the definition and ensure that you don't have any extra degrees of freedom. This equation plus these constraints guarantee that the object you're describing is a spin 3/2 fermion. The normalization is fixed, just like for normal Dirac spinners. And I can construct a positive energy projection operator, just almost like the way I did for normal fermions. I just have a projection operator R, which has a simple form. This is just a bit of algebra. You can work with this very easily. Use the completeness relations, do the contraction of indices, and it's straightforward. I have Faddeev amplitudes now to be computed in the contact interaction using the static approximation. Because I'm using the static approximation and the contact interaction, I can't have relative momentum dependence. That very much simplifies what my Faddeev equation is going to be and what the outcome will be. Because I have 3 up quarks, there's only one term in the kernel. I have 2 up quarks in the diquark and an up quark down here. All that can happen is one of the up quarks from here can come and join the other one. So there's one term in the kernel. Here it is, what you've seen. I'm solving for the Faddeev amplitude. I have a diquark propagating with a quark. They're both up. This is an up-up correlation, that's an up. This one breaks up, the quark goes across, and it recombines. And I'm using the static approximation, so there's no dependence on the relative momentum here. From that, you have a very simple algebraic calculation to do. You use those Clifford algebra relationships I gave you. You use what I've defined above, which is simple one-dimensional matrices, and you can derive this expression. That's the Faddeev equation. Just a simple algebraic expression for the delta baryon. There are a couple of things you can see very quickly from this. The coupling into this channel decreases as the mass of the quark increases or the mass of the diquark increases. This tells you that the mass of the bound state is going to get bigger if I make the mass of anything in the bound state bigger. How much more transparency do you want? This is a very clean way of seeing that if you solve the Faddeev equation and you make the mass of the constituents heavier, the mass of the bound state is going to get heavier. Another one. This term here is the correlation amplitude for the diquark. If the diquark correlations get stronger, then this gets bigger. That means the mass of the bound state will go down. So the stronger the correlation in the diquark channel, the lower the mass is going to be of the bound state. So these are the sort of insights you can draw by doing a contact interaction. These are real features of bound state physics. You make tight correlations, then they pull the bound state systems down. You make loose correlations, they get more massive, and the mass of the bound state goes up. You can solve that equation. I used Mathematica for it. And you see something very simple. Delta baryon mass is rising basically linearly with the mass of the constituents. It's a very simple bound state, the delta. If I take the ratio of the delta mass to the sum of the masses of the quark and the diquark, I get something which is almost 1. There's a very small amount of binding energy produced by the quark exchange. All the binding energy is coming from forming the diquark. And then I have a bit of residual exchange energy coming from the diquark exchange. Is this realistic? Almost. Real quark exchange is dynamical. It provides more attraction, so there's a bit more binding energy. But what I've done is I've tuned this parameter, where do we have it, G delta here, to make this more realistic. And you can do that too. These are real features of the physical baryon spectrum. Okay, simple models are useful, but you can do better. And you need to do better if you're going to connect with the real world in any real way. You want to put this feature into the Faddeev kernels. You can do that, and you can compute a proton wave function. How do you compute wave functions? You solve a Faddeev equation. How do you interpret wave functions? Well, you go to the light front, because only the light front has probability interpretations, as we've seen. This image is a lattice simulation of the leading twist PDA of the proton. This triangle diagram is a barycentric plot, and just like the pion has a conformal limit profile or an asymptotic profile, which is 6x, 1 minus x, What that says is the quarks are very simply correlated. There's an analog for the three-body problem. And the analog for the three-body problem is just 120 times x1 times x2 times x3. I could equally have written this formula as 6, that's not working, x1, x2. Momentum conservation says that x2 equals 1 minus x1. So you see that dropping these corrections to the conformal limit or the asymptotic limit just gives me an obvious analog of the pion. The probability is particle 1, particle 2, particle 3. The pion is particle 1, particle 2. And that's a symmetric curve in this three-dimensional plane, which peaks at 1/3. That is, you take 1/3 along here, 1/3 along there, 1/3 along there, and the thing will peak in the middle. A shift in the location is telling you about correlations in the system. If there were no correlations in the system, this thing would still be peaked at 1/3, 1/3, 1/3. It could be broader, it could be narrower, but that would just be about how the three quarks are being affected by the mean field. But if it's shifted, then you're really breaking up this symmetry between the three particles. And that means you're putting correlations into the bound state. So the methods one has used for the mesons can be extended to compute the pointwise behavior of baryon PDAs. This is work that Cedric did on baryon PDAs. This is the conformal limit result, 1/3, 1/3, 1/3. You now go to the nucleon realistic, and you consider a scalar diquark, and you see the clustering is skewing it down to the right. Scalar diquark, activated diquark together, you put them in there, this peak is shifting, just like it does in the lattice simulation. So by having this continuum approach, you can understand what the skewing is doing, or where it originates in the wave function of the proton. The benefit of having a continuum approach is that you can also calculate the PDA for the excited state proton. And what you see is that the wave function has a line of zeros in it. This is the result of a fully Poincare-covariant calculation of the Poincare-covariant wave function for the proton's first radial excitation. You know from quantum mechanics that if you solve a Schrödinger equation, you look for a radial excitation, that excitation has 1 0 in its wave function. Ground states look like that. The first excited state goes through 0 and comes up. Here you see that exactly the same thing is happening in the leading twist PDA for the proton's first radial excitation. It has a line of zeros. It's peaked sharper because this thing is normalized to 1. If I have a domain of negative support, then the part that's positive must be taller. So you get this whole picture of correlations. This excitation's PDA is not positive definite. It's a prominent line of zeros. So you can now understand the incipient lattice studies of baryon PDAs in terms of physics that we understand. The agreement between the lattice and continuum results only happens when you have both scalar and accelerated diquark correlations in the nucleon. If I neglect the activated diquark correlations, I have a very poor correspondence between continuum and lattice studies. The only way to understand the proton properly is to include the active-vector correlation. This is a statement about continuum QCD and lattice QCD. They both concur on the importance of the active-vector diquark correlation. This is important because when people have been making models in the past, they've called the scalar diquark the good diquark and the active-vector diquark the bad diquark. And they like to ignore the active-vector diquark. You can't do that. QCD drives the active-vector diquark into the proton, and it plays a dynamical role that you can measure empirically. The proton's PDA is a broad concave function. Its maximum is shifted relative to a peak in the conformal limit or the asymptotic expression, and both scalar and active-vector diquark correlations are critical in the proton. There are no humps or bumps in the leading twist PDAs of ground state S-wave baryons. Again, there was a big argument 30 years ago that it was evolving until the last few years when we said no, end. The bound states are simple. Their wave functions don't have structure of that type. They are concave functions for baryons in their ground states, just like they are for mesons. They originate with dynamical chirosymmetry breaking in the standard model, the same type of physics. And as I've argued, that's the same physics that drives the confinement phenomenon. Let's see. Perhaps I'll do that. The scattering problem we've talked about a bit, and we mentioned that the electron has a very simple current, and the proton has a more complicated current involving two form factors, the Dirac form factor and the Pauli form factor. And we saw that if the proton was simply structured, then GE and GM would be the same. That's the point. For a simply structured fermion, the charge and magnetization distributions would be identical. You can address this question now using these continuum approaches to the bound state problem. Because it's a Poincare covariant approach, you can hit the target with as much energy as you like and still compute the process without resolving the bound state problem, because you have full Poincare covariance. You have the wave function already, I've illustrated that. What you need now is a current. The photon has to strike the proton. How does it interact with the proton? Well, it strikes a quark, or it strikes the diquark. When it strikes the diquark, it can make a transition. The diquark can change from scalar to axial vector. What you need as well are these final three diagrams. Now, in a contact interaction study, these diagrams aren't there because momentum doesn't get exchanged. And you have a very simple calculation of the form factors, and it has been done very usefully. And what you can learn is a great deal about the qualitative features of form factors, radii and so forth. What you find also is if the interaction is different to that which occurs in QCD, then the form factors will have different behavior. The form factors you obtain for the proton using a contact interaction will have a certain power law behavior. In fact, it's very hard. And I can make the interaction weaker than QCD. I can make it 1 over q to the 4th instead of 1 over q squared. Then the form factors will be very soft. You can demonstrate this, and so that means that you can use experiment now as a measure of just what the 1 over q squared behavior is for the form factors, for the theory, for the interaction. When you have a realistic interaction, these diagrams become 8-dimensional. The only way to compute them is using Monte Carlo methods. So it begins to become a numerical problem. A standard laptop can still do it today, so it's not so hard. The more complications you add, the longer it takes. And if you drop the quark-diquark approximation, it can become difficult. Still achievable with a small cluster overnight, but not achievable in hours on a laptop. The reason is that for a Faddeev amplitude in the quark-diquark approximation, the proton has 8 different functions. We saw the pion has 4, the proton has 8. If you drop that, you end up with 128 independent functions. And they have to be translated, overlapped with the other. The current becomes very simple, but the wave functions pick up a lot more complexity. But that's what we are doing now. It's a natural way to go, because you want to see how the diquarks emerge dynamically from the scattering process. So it's a natural thing to do, and it is achievable in finite amounts of time. Anyway, you can compute the form factors this way. What I've illustrated here is the direct calculation in comparison with an empirical parametrization. And you can see you do a very good job. This quark-diquark picture with scalar and axial diquarks describes the form factors extremely well. This is the other point I was making. You compare the contact interaction results with the correct results, the fully momentum-dependent results, and the data. See, the contact interaction is good at small q squared. You knew that had to be the case. I said that yesterday. So long as the momentum of the probe does not exceed the gluon mass, then this approximation of a contact interaction is going to be reliable, because a long wavelength probe is not sensitive to the running of the coupling. But once the probe becomes more energetic, it gets a smaller wavelength and it starts to be sensitive to how the couplings and wave functions run. So you see that the contact interaction can be useful in the neighborhood of q squared equals 0, but it should not be used for larger q squared. Yeah? No, these ones are not divided by dipole form factors. If I wanted to expose small-scale fluctuations that might be might owe to more complicated physics, then I would have used a dipole divider. For example, at small q squared, all sorts of meson-baryon final state interactions have an influence on how form factors truly evolve. And we haven't included those things here. So to expose them would just open up a new set of questions which I'm not able to answer in the time available. So we momentum-independent Faddeev amplitudes paired with momentum-independent dress quark mass and beta subfield amplitudes produce harder form factors which disagree with experiment. So it's obvious it's a 1 over q squared theory. Right. The ratio of the proton's form factors is now where we can go. This was what the picture looked like before 1999. This slack result, this high-energy physics result, that the ratio of the form factors was a constant and it was 1. That used a simpler technique to try and extract the form factors, so-called Rosen-Booth separation, which I'm not going to describe in any detail, but it's an indirect way of extracting the form factor ratio. You get GE and GM separately, and you get errors creeping into GE as q squared becomes larger. So you can expect perhaps that something's wrong with GE from this extraction. JLab, with their polarization transfer measurements, have measured this form factor, this ratio. It's a very different picture. The results that we have from the continuum studies present this picture. If the quark mass function is momentum independent, I get the dashed line, and this ratio goes through 0 very quickly. I'm going to explain why this is so soon. If you have a momentum dependent mass function, then that's the way the form factors look, the ratio looks. So it does go through 0, quite probably. This was an old parameterization of the data before they put in the sort of ratio of the form factors from JLab. And that parameterization of the data does not go through 0. So this indicates the proton has a very rich structure. The difference between that extraction and the JLab data is believed to be associated with beyond Born approximation scattering effects. So in one photon exchange experiments, or if you analyze the experiment using one photon exchange and use the Rosen-Booth separation, you get this set of results. If you correct that for 2 photon exchange physics, then the Rosen-Booth results can drop down. So it looks like, phenomenologically, that the difference between the 2 extractions can be explained by corrections to one photon exchange approximation, which are more important when you analyze the data using the Rosen-Booth separation, because the Rosen-Booth separation is not a direct measure of the ratio. The question we're asking is, does this ratio pass through 0 at all? As you've seen, these continuum functional methods predict that it does go through 0 with the mass functions and so forth constrained by meson physics. But you have to ask another question. Suppose some of that was wrong. Is it a necessary thing that this ratio always go through 0, or are there circumstances under which it does not go through 0? What is the driving physics? I could have wrote something on the board. This ratio involves GE and GM. GE and GM. GM is the sum of the Pauli, of the Dirac and the Pauli form factors. For the ground state spin half object, both of these form factors are certainly not non-zero. They're certainly positive definite. So Gm is always going to be positive. Ge is F1 minus Q squared over 4m squared times F2. So that can go through zero, depending on just how F2 compares with F1. And not just F2, but Q squared times F2. When you analyze the high energy limit, the large Q squared behavior of F1 and F2, you find that F1, the Dirac form factor, behaves as 1 over Q to the 4th, and F2 behaves as 1 over Q to the 6th. That means Q squared times F2 will be 1 over Q to the 4th. So it's conditional. This can go through zero. It doesn't have to go through zero, but it can. The Pauli form factor is a gauge, this one, of the distribution of magnetization within the proton. Ultimately, this magnetization is carried by the dressed quarks, and it's influenced by the correlations amongst them. And those things are expressed in the Faddeev wave function. I'm plotting here then F2 for the proton divided by F1, the two things that appear in this expression. If the dressed quarks are described by a momentum-independent mass function, then they behave as Dirac particles with constant Dirac values for their magnetic moments, and they produce a very hard Pauli form factor. And that's why, when you compute this ratio using the contact interaction, the ratio goes through zero very quickly. The alternative is to suppose the mass function is momentum dependent, as we know it is. That means that the quarks would have a very large magnetic moment at small q squared, but have no magnetic moment at large q squared. This is a statement of symmetry. Massless fermions cannot have an anomalous magnetic moment, because the term that would describe that action violates chiral symmetry. So the generation of an anomalous magnetic moment for a fermion is a consequence of chiral symmetry breaking. So when the chiral symmetry is broken dynamically, then the strength of that anomalous magnetic moment can change with momentum transfer. That's what this says. At small momenta, the quarks behave like they have a large magnetic moment, and that magnetic moment disappears as the probe momentum gets larger. In that case, the evolution changes completely. This ratio no longer rises, but it falls away. And that is the explanation for this behavior. So from this perspective, the existence and the location, if it does exist, of the zero here are a fairly direct measure of the location and width of the transition region between the non-perturbative and perturbative domains of QCD, when the mass function changes from being large to being small. If the mass function is hard, the zero is here. If the mass function is soft, it shifts out here. So one can anticipate that a mass function for the quarks could exist in which the quark very quickly becomes partonic. And in that case, there'll be no zero at all. So that means there's a very constructive opportunity for feedback between experiment and theory. Locating this zero, finding if it's there or not, can tell you in a fairly direct way just how rapidly the quark mass function runs. So again, not a direct measure of the mass function, but a measure of a moment of that mass function. And that's what you see here. The dressed quark mass function, it was chosen to just change the intermittent behavior by an apparently small amount. This says, okay, suppose the quarks don't run quite so quickly to their asymptotic limit. What happens to this ratio? Well, it had a zero, but as I make the quarks become partonic more quickly, that zero disappears. So this is a quantitative demonstration of those qualitative ideas. The zero may or may not be there in the proton electric form factor, and whether it is or not And where it lies are a measure of just how rapidly this quark mass function runs. The proton has a partner, it's the neutron. I can do the same analysis for the neutron. If one accelerates the rate at which the dress quark sheds its cloud of gluons to become a parton, then the zero in GeP is pushed to larger q squared. That's what this shows. Normal quark propagator, I soften it, and I make the zero disappear. The neutron goes the other way. If I change the quark propagator in just the same way, the neutron zero comes in. So these things will be tested at JLab. There will be a zero in the neutron's electric form factor. You can't avoid that one. And JLab at 12 GeV will push to q squared where it will be seen. The correspondence between these two things will tell us a great deal about how the mass function runs. Because the down quark is doubly represented inside the neutron, and the up quark appears only once, there's a different weighting of the charges. So the neutron will always have a zero in its form factor. And what's more is that there's a prediction that at q squared of about 5 times the nucleon mass squared, the electric form factor of the neutral neutron will be bigger than the electric form factor of the charged proton. And that will be verified or tested at JLab at 12 GeV squared. Now, I think I'm going to wrap up, really, because there's so much more I could say, talk about hybrids and so forth, but I don't think I will. Let's see. Go there, and we'll go here. So I've given you a tour of the application of continuum methods to QCD. I've given you a couple of exercises using a contact interaction so that you can realize with your own hands the sorts of things that you do to solve these problems. The contact interaction is simple. It has some qualitative features that QCD shares. The techniques are basically the same. When you go to more sophisticated interactions, it becomes more complicated. You need computers to solve the problem. Nonetheless, the ideas are still the same. The correlations exist inside the proton's wave function. Those correlations exist in all bound states. And as we're just showing now, that even in bound states with a heavy quark, diquark correlations play a role in a special way that you can compute. Our challenge was to explain and understand the origin and distribution of the vast bulk of visible mass. Our current paradigm is quantum chromodynamics. I have described why QCD is plausibly a mathematically well-defined quantum field theory, the only one we've ever produced. So whether or not you care about QCD as a theory for the strong interaction, you ought to care about the fact that this is probably the only mathematically well-defined quantum field theory that you will ever see. So it's worth solving. It's worth learning how to solve it. The challenge is to reveal the content of strong QCD. If the theory is essentially perturbative, such as electroweak theory, it doesn't really matter. Perturbation theory is achievable. You can solve it up to some finite number of orders. And if you never need to go beyond that number of orders, then it's not an experiment worth doing, because you've validated it already. This is a very tough problem. And as I said at the outset, the way we solve this problem today is by collecting everything we can do from experiment, phenomenology, and theory. No one is absolutely right. We need to draw everything together and distill the best from all of those approaches. And that's what the practitioners today do. They will argue, sometimes the arguments are silly, but the elements of discussion are essential to avoid a dogmatic approach to this problem. You have to keep an open mind, and as an experimentalist in particular, you listen to the arguments, and you have to decide for yourself which ones seem most plausible, and then proceed to test them. This type of thing will be necessary to continue into the area of, or the era of JLab at 12 GeV and an electron-ion collider. So thank you. I finished.
to thank you for such a beautiful and charming tour in the Schwinger Dyson country. And I hope that these fruitful seeds that Craig left in our mind and brain produce new ideas. You are our youngest colleagues, and therefore the next step will be your duty. Okay, let me thank again.
Thank you very much, Gianni.
Thank you for coming.
Thank you. It's very good. Thanks a lot.